Hi, this time we are going to design a patch antenna. You are seeing just half of the structure here. This is the complete drawing inside FEKO. The patch antenna is a planar antenna. It's a very popular antenna. As you can see here, we are designing just half of the structure. This is a planar structure here. So this is the feed line. It's going to be excited by a microstrip line, which has a length called feed, and also which has it's a square patch antenna, just for make it easier to draw, and it has a size of this variable called size. Um, what determines the resonant frequency is the size, specifically this thing here, this dimension here. So it's supposed to be half wavelength, guided wavelength, to the frequency you are interested in. And if in order to match the input antenna impedance 250 ohms, one usual way to achieve this is to use this called inset. So right here on the edge of the patch antenna, we have something around 100, 200, 400 ohms, depending on the structure, depending on the thickness of the substrate. And right on the middle, we have 0 ohms. It's a short circuit. So we start from here, which is 400, 200, to 0, to a short circuit. So we need to penetrate into the patch here in order to reach the 50 ohms. So that's the basic idea. And this the length of how far you penetrate inside a patch is called inset. So just to summarize, size, this dimension here determines the resonant frequency, and the inset here determines the resonant impedance, which is supposed to be 50 ohms. So our procedure to design this thing inside FEKO, we are going to inform FEKO all these 8 points. Of course, the 8 points are defined by these dimensions here, these variables, as FEKO calls. And then we can design just half of the structure, and using mirror, we can design the other half. It's one of the simplest ways to design this structure. So the first thing we need to compute here is this width of this microstrip line in order to achieve 50 ohms. So we can reach any one of those websites here, for instance, this EMTalk. And let's suppose we are going to use a substrate which has a dielectric constant of 3.4. Let's say we have a substrate height of 1.6 millimeters, and let's say our interest frequency is 5.8 gigahertz. This is the resonant frequency you're looking for. We are interested in 50 ohms, and let's say 10 degrees of electrical length. It doesn't matter for us, we're just interested in the width. So here we can see that our W50 variable here, W50, is more or less 3.68 millimeters. Then we can just jump to FEKO. We create a new model, and as usual, we define all the variables. The variables, again, they are extracted from this thing here, this drawing here, this model here. Okay, let's do it. First variable is, of course, the frequency is 5.8 times 9, 5.8 gigahertz. Second, it's wavelength, which is C0 over freq at. Next is the size. The size is the resonant side of the patch antenna. It's supposed to be half guided wavelength. So just to get an approximation here, just to make it easier, we are going to define it as wavelength over 2 times square root of 3.4. 3.4 is our dielectric constant. This is not quite the correct effective epsilon of the material, but just a first approximation. So it's complaining because this is wrong. Wavelength. Now, there we go. Okay. This is the size of our antenna. Next, the feed length, let's say it's wavelength over 2. This is the size of this small arm here, this microstrip line. Wavelength over 2. Let's say the next is inset. Inset is size over 3. This is a practical value that I usually take. Add insetw. This is size over 20. It's also a practical value. And W50, this is the width of the microstrip line. We just computed as 3.68 times power of -3, which is 3.68 millimeters. Minimum frequency, let's say, is 4 gigahertz. Fmax is 6.5 gigahertz. And finally, the thickness of our substrate, as defined here, as you will call it, where is it? 1.6 millimeters. 1.6 millimeters. Yes, everything was correctly set. Then we start designing our antenna here. We just follow these points here using the polygon. And this polygon I will leave in the description part of the video, but we are going to do like this. We're going to polygon, first point, corner 1. I'm just following these numbers here. First is, of course, the origin, 0, 0, 0. Second point is 0, feed plus size, 0. Corner 3 is minus size over 2, feed plus size, this is the third, and n is all the time 0. 4 is minus size over 2. I can copy and paste from here, Control C, Control V. The V corner 4 is just feed, 0. Corner 5 is again minus 0.5 times W50. The V is here, I have to subtract inset W. And 5 is feed, and here is just 0. And corner number 6 is the same here. Control C, Control V. And here is feed plus inset, and is 0. Corner 7 is minus W50 over 2. Feed plus inset, Control C, Control V, 0. And finally, the last one is copy and paste, minus W50 over 2, 0 and 0. Okay, it created. You can see here our antenna, half of our antenna was created. Now we need to create the medium, which is our dielectric. We just type in media, right click, dielectric medium, We should have created some variable, but just forgot about it. Just type in 3.4. Again, it came from here, 3.4. This is the epsilon r of our substrate. Add, close. And now we start designing our substrate. Our substrate, we type in cuboid. You see here how the cuboid is supposed to be oriented along those axes. Base corner, again, Ctrl Shift. We select this point here, extreme, and Ctrl Shift here, here, and now we can just click anywhere for the height. And now the trick is height here, we just type in h sub, and you just add here, for instance, minus, and here we have to subtract 1 millimeter. This is a kind of a space, free space between the substrate edge and the antenna. And here we just give it, for instance, 1 millimeter. Maybe it's too small, we can make it 2 just for the sake of security. The simulation is, of course, longer. The bigger the larger the substrate is. And I think that's it. So the regions. Now you can see here that my video is not as good because the way I changed, you don't see the antenna. It doesn't matter. We just need to click here, right click in properties and say that our region is the dielectric one. And now we just make the mirror operations for this antenna here. We select the polygon and we come here in transform, copy and mirror. You see the trick here, you just click under work plane, and by changing here, you see, you just see the ghost of the mirrored antenna here. That's the way to go. We don't need to worry about anything else. Just click OK and it's done. And you do the same for the cuboid. The cuboid, copy and mirror. We do the same. We just jump to the work plane. You keep on clicking here. There you go. And you can see it's what we're expecting to have. Okay. You see? Then you have your antenna designed here. This is correct, the region 1. Our polygons, they are supposed to be all the time PEC, right? PEC, which is perfect electric conductor. Here, properties PC, right? We need to create our feed point here. For that, like the microstrip line video, we need to create an extension of a U-shaped metal part here connecting the microstrip line to the ground plane. So the easiest way to do this, we just go to construct, rectangle, and we select this point here, base corner, and here we just type in W50 and depth here we just write H sub, right? Something is wrong. W50 should be minus, minus, so it goes outside. No, it's not this, it's H sub minus, so it goes outside. There we go. H sub. Great. Done. Now we don't need to do the same for the part down there. We just go to transform, copy and translate. From, we pick Ctrl Shift this middle point here and this middle point here. There we go. Okay, we have both things, both U-shaped feed port here defined. We need to connect them here to create the other part, rectangle. We just go here We just change the orientation. There we go. Geometry, Ctrl Shift base corner, for instance, we select this point here. This is the width. We select what? This point here. And for the depth, we select this point here. I guess it's correct. Create. This is the last rectangle. We just need to move it because it's touching the substrate here. We just need to move it. It's much easier just to make it translate. From Ctrl Shift here, Ctrl Shift here. Create. There we go. It's done. Easily done. Right? All of these guys, they should be set to PC. Just checking on them, apply. This one here is properties PC, just for the sake of security, to be sure about it. Properties PEC. There we go. This guy here we need to use to create an edge part. We go to Home, we go to Split. It's asking where is this work plane. The work plane we just align here, and we just make it like a knife. You see? There we go. It's cutting this metal sheet here as a knife. You just type in create. Now we have two different parts. We just need to do a union operation, and now selecting both faces, we can say it's our edge part. This guy here is the negative point. It's created. Our part, edge part, is created. We just attach a voltage source to it. There we go. And we create our ground plane. Our ground plane is very easy. We just need to select the cuboid, this face here. You just change it to PC. Apply. And also this here, this is the same properties, PEC. It's finished. Yes, our structure is correctly defined. Just we need to tell FEKO that all these elements are connected, electrically connected, otherwise FEKO doesn't know. We just select all of them with Control, and we go to Construct and Union. You see, everything now is connected. Everything is, FEKO knows that everything is connected. Now we need to tell FEKO that our frequency is from Fmin to Fmax. Let's say 11. Might take a little bit too much. Let's say 21. Okay. We go to mesh. We create a mesh. Though FEKO does that for us, we don't need to worry about it. And what else? We can just go to CM validate. Seems okay. And of course, I forgot, ask for the far fields. Create. We can ask for currents, for instance. Create. I guess that's pretty much. Then you can ask for near field if you want, but for a while, I think that's pretty much everything we need. Just make invisible this big ball, and we can type in FEKO solver. We give it a name, patch 2. So it's finished. We just jump to post FEKO. Let's see if our antenna is right. First thing, of course, we need to take a look into our Cartesian plot and just drag and drop the voltage source. And that's fine. You see, exactly as expected. We have a very strong resonance, not on 5.8. We just come here to measure, and we get these lines here. We have not exactly at 5.8, but it's 5.6. How did it happen? These results here, these dimensions here, inset size over 3, its experience, it gives more or less 50 ohms. You can play around and change the size and get a correct resonance frequency shifted to 5.8. You can see also under here Smith. You can just drag and drop voltage source, and you see it's very broadband. We don't have enough points, but we can see that we're pretty close to the center of the chart, which is the Smith, which is the matched point. We can see the currents. The currents are all the time nice to take a look at it. Just drag and drop here. You see, this is the 4 gigahertz. Just view, top, there we go. And we can take a look at instantaneous magnitude in dB. And under animate, you see this is it's sweeping the frequency. And if we go to close 5.8, it's more or less here, and we play, oops, not this, 5.8 here, and we just select phase. We are just seeing 5.8. You see how the fields develop at this frequency, at this resonant frequency, 5.6 actually. And you can see how the fields are organized for this frequency. We have one maximum here on the middle, but it's a half guided wavelength across this. Actually, it's a cavity here below the antenna, right? And this inset was placed so that the feed line penetrates where we have exactly 50 ohm on this point, more or less 50 ohms. It's because it's an antenna, it's all the time nice to see the far field. Just drag and drop. It's nice to right click here, and under visibility filter by medium, we select all these things here and we make it invisible. So you can see here how the field is for our resonant frequency, which is more or less 5.6. You see we have a total gain of in dBs, 9 dBs. This is kind of misleading because we are counting, FEKO also takes into account the spurious radiation from the microstrip line. Maybe our microstrip line is too big. This is something that you have to play around with to see how it affects the structure. Don't you forget that you need to place a connector here. The connector is, depending on the frequency, is pretty large in comparison to the patch. But this is a trade-off. Only the real world will show you what the best result is. And this is the far field. We have more or less 9 dBs. It's a kind of high gain. And you can see here how it works in this direction. Of course, most of the radiation goes upside because we have, just coming back here, most of the radiation goes upside because we have the ground plane here. And the ground plane here kind of reflects all the energy upwards. That's it. I hope you enjoyed. I hope you had nice results. Thank you very much. See you next time.